So now I'm looking at our first example again. So this one is the one where we did have a trivial null space, and we only had the equilibrium solution at the origin. And now I'm going to modify it. So I'm going to add 3 here and subtract 6. So what has changed? This is now no longer homogeneous, right? If I write it out as like a linear operator being applied to the vector x, it's this linear operator. So that's like my L, and it's being applied to x of t, y of t, in order to give me not 0, but 3, negative 6. So this is my differential equation. L applied to x equals, and then a constant non-zero vector, 3, 6. Okay, so non-homogeneous. All right, well, I can ask the same question here. So what are the critical points? So here's an easy way to write this. How about like this? X equals ax plus b. X prime equals ax plus b, sorry. Where, and then I just say what a and b are. A is 2, 1, 1, 2, and b is 3, negative 6. Okay, so now I don't need to bring in these numbers until they're needed. I encourage you, anytime you can, write things in sort of a more compact way to do that. So what are the critical points? So critical points satisfy right-hand side equals 0. Sorry. Like that. This is the right-hand side. If x star is a critical point, then it's just a constant that satisfies this. So what satisfies this? Well, it's the set of things that satisfy this. Right? So in our search for a critical point, we write down this equation, which is this equation. Okay, so it's just this. That's one way to look at it. If A is invertible, if A is an invertible matrix, if A is not invertible, so here we know A is invertible, right? Because we already studied this matrix in this earlier example here, and we checked the determinant. The determinant is 3. It's not 0. So this matrix is invertible. So we can totally do this. You can solve by hand if you want to, but why would you? Maybe something you do like once or twice just to get a little bit of practice, and then better to just stick this into a computer. Okay, so this is how we get our critical point, and there's just going to be one. Now, one example that I'm not going to show, but that you can also figure out if you ever run into it, is if A is not invertible, then you will get for your critical point, you will get a whole line of equilibria again, right? And then you will not be able to solve the system by just inverting the matrix A. You'll have to actually solve it and find what is the line of solutions. This is the sort of thing you learn how to do in Math 4A. And if it comes, we'll look at it if it comes up. But basically, you just find the solutions to this. So one way to do it is find the solutions to the homogeneous version, right? Now, homogeneous used in the sense of linear algebra, linear systems, rather than differential equations, linear systems. First solve this, then find one solution to this non-homogeneous, and then add them. That's one approach. Okay, but here, A is invertible, so we have this easy route. Okay, so what is actually x star? How about I go to Mathematica? Just quickly do this here. So A is two, 1, 1, 2. B is, and everything I'm doing in Mathematica, you can do this in Wolfram Alpha, or Wolfram Cloud, or whatever. And yeah, there are many programs that do this kind of thing, other than the Wolfram series of stuff. So just if you're just using Wolfram Alpha, maybe you can't define variables like this. You would just have to type everything out every time. It still saves you a lot of work, though. So inverse of A, so I can look at what that is. Oops, I have to run this cell. I have to look at what that is. Interesting. Guess I don't really care that much. I want negative inverse of A multiplied by the vector B. And I get negative 4 or 5. Cool. So there's my one critical point. So if I have a solution starting at negative 4 or 5, then it'll stay there forever. So this is my one equilibrium solution. How to write this? X of t equals negative 4, y of t equals 5. That's the only equilibrium solution. Any other initial conditions other than negative 4 or 5, you're going to get movement. Now, the reason I'm giving special attention to this case is because I want to show you that you can actually turn this into a homogeneous linear system. This is valuable because we're actually going to spend pretty much the rest of the course studying homogeneous linear systems. So if you can convert these ones to homogeneous ones in a systematic way, then everything that we're doing also extends to these. So how would you convert this to a homogeneous linear system? So let me sort of summarize the info here. How about I just erase all this scratch work? And just write down the final answer. We got x star equals negative 4, 5 is the only critical point. So to turn this into a homogeneous linear system, do a change of variables. So you can define a new variable, let's call it u. So define u to be x minus the one critical point. Or if you have many critical points, just pick one, any one, and then do this. So u will be this. So let's use the symbol u to denote the package of two new variables, uv. So the way I phrased it is I'm introducing one new vector variable, but I'm really introducing two new variables. Let's call them u and v. So then this is, u is going to be x minus negative 4, so x plus 4, and v is going to be y minus 5. So I'm introducing two new variables. U is x plus 4, v is y minus 5. Then rewrite this differential equation, but in terms of the new variables, u and v. So what would you say about u prime and v prime? Let me write it like this. What would you say about u prime, which is u prime and v prime? It's the derivatives of these. Well, the constants don't affect anything, right? Adding a constant does not affect the derivatives. It's the same as x prime and y prime. So the left-hand side of this differential equation just reads u prime, v prime. And then how does the right-hand side work? So let me package things like this to see. So right now, as it stands, in terms of x and y, here's what the right-hand side looks like. Right, it looks like this. Now, if I want to replace x, the xy type stuff by uv type stuff, I should use x equals u plus x star. That's what this says, right? Just rearranging. It says x is u plus x star. So let me go here and replace the x by, not forget this, and replace the x by u plus x star. And I promised you this would end up being homogeneous. So let's see. This is a u plus a x star plus b, right? And now I regret erasing it, but what was special about x star, I erased it, but what was special about x star is when we said it's a critical point, that ended up meaning that a x star is negative b. That's what was special about x star. So a x star is negative b. So this is a u plus negative b plus b. So it's just a u. Okay, so the overall differential equation we ended up with is u prime equals a u. And that's homogeneous. So there's no constant stuff getting added. There's no other stuff getting added here. All right, so the change of variables that worked here was going from x to x minus a critical point. And I guess it's not really too surprising that that's something that would work, since we know that for any homogeneous linear system, you just have an equilibrium solution at the origin, at 0, 0. For this non-homogeneous one, you end up with an equilibrium solution at -4, 5, right? So by doing this, we just kind of shifted our phase plane. By switching from xy axes to uv axis, we just did a translation and moved our axes, moved our coordinate axes, so that they're now arranged so that the uv origin, u equals 0, v equals 0, is where x equals -4, y equals 5 is located. So we just moved our coordinate axes so that the origin is now where the critical point is, and it became homogeneous. So here's the picture I'm getting at. Initially we had these xy coordinate axes, then we've got this point -4, 5 over here, and then we created the new uv axes centered here. And then how are uv related to x and y? It's a translation by this vector, which is the critical point location itself.